Hi everyone. Today I'm going to talk about LazyLog, which is a new shared log abstraction for low latency applications. So before I begin, some of a background, I'm Ram. I'm an assistant professor at the University of Illinois, Urbana, Champaign. I co-lead a research lab called Distributed and Storage Systems Laboratory. I previously was a consultant researcher at VMware. I also did my postdoc at VMware Research. Prior to that, I got my PhD in CS from the University of Wisconsin. So before I begin, all the work that I'm going to present today was done by this incredible and talented set of PhD students, and this was also led by another faculty member at UIUC, and I would like to thank the US National Science Foundation, IBM, and ATAP for funding our work. So what does our group do? Our group is predominantly a storage systems and distributed systems group. We work on a bunch of research on all of these topics ranging from fault tolerance, reliability, recently memory disaggregation and storage disaggregation, vector databases, and shared logs and data streaming. We have published a bunch of papers in all of these conferences. You can read all of this work. It's publicly available. Some of these papers have won awards at all of these prestigious academic conferences. So I'm not going to talk about all of this work that we did in our group. This talk is about logs. Logs is something that every developer is used to. So that's what this talk is about. When I mean by logs in this talk, what I really mean is systems like Kafka or services built on top of Kafka, offering Kafka as a service like Confluent or WarpStream or Pulsar or Red Panda or so on. And you can think even every cloud provider today offers a similar service. Like, for example, Kinesis. It's a Kafka-compatible streaming API, right? This is what I mean by a log. And there are also academic and industry versions of these offerings, right? Like, for example, Carfu, Scalelog, and many of these academic prototypes, which kind of essentially build a log. And this view is not controversial at all, right? So some of the systems, when you talk to people, they may think this is like a pub sub system, a messaging system, a streaming system, and so on. All of these views are correct. But at their core, they're essentially a distributed shared log, right? And this view is not controversial at all, right? So there was this very famous blog post from Jay, where he argues why the real-time data's unifying abstraction is that of a log, right? So essentially, all the systems that I showed in the previous slide, they export a log interface, right? And you can, the log gives you this very nice abstraction of a fault-tolerant, durable, and ordered sequence of records, right? You can do two basic operations on this log. You can basically append data into the log, given record, and then you can read offsets into the log and consume the data out of it. More specifically, if you look at the interface for append, it's pretty simple. You give a record, you get an integer back, which is the position in which the record was appended into the log, right? And the read interface is also pretty simple. You give a position, and then you specify saying something like, read these many logs starting at this offset. And then the log just gives you those records. That's the pretty simple contract that the log gives you. So in the outline for the rest of the talk, what I will convince you is that despite years of research and we all building new logging systems and new data streaming systems, there is a pressing problem for today's shared logs, which is high latency. And when I mean high latency, I mean both high ingestion latency and high end-to-end latency. We'll see how we can fix both of these problems. But this talk will focus mostly on the ingestion latency, right? And in the second part of the paper, I'll show you how we can rethink how we construct these shared log systems, and I'll propose a new solution called LazyLog. It's an academic project which was built at the University of Illinois. It was published in this conference called SOSP, which is the top-tier systems conference, and it won the Best Paper Award there, right? And LazyLog cuts down ingestion latencies by an order of magnitude compared to existing systems. And LazyLog is as an abstract idea. It tells you, here is how you should think about how to design a shared log. But then you have to really implement the system. So we had multiple designs of the LazyLog abstraction, and we did two particular designs that I will talk about today. And in the last part of the talk, I'll describe this design, and then I will show you how these designs improve application performance. So let's get started with the first one. But by the way, if there are any questions, feel free to interrupt me at any point. So to set up the context, I need to give some background, so bear with me here. This is probably preaching to the choir because most of you know what's happening in the slide here. So when Kafka-like systems give you ordering, what they give you is something called the linearizable ordering. What this essentially means is that if append B starts after append A is completed, then B must appear after A in the log. This is the linearizable ordering. And many systems like Kafka, Red Panda, or any other open source shared logs that you can think of, they provide ordering only within a particular shard. So when I mean a shard, what I want you to think about, a shard is a fault-tolerant unit which keeps your data durable within that shard, either by replication or some other way of keeping your data durable, something like erasure coding, right? But for now, assume that a shard is a multi-way replicated system that is replicated using Paxos, Raft, or primary backup, or whatever, and then it stores your data. And Kafka-like systems cannot tell you the ordering across shards, right? So it gives you linearizable ordering within the shard, but it cannot tell you here, for example, whether the first record of shard 1 comes before or after the records in shard 2. It cannot fundamentally do that. But you can scale your Kafka throughput by adding more and more shards, but you don't get total order. So this conquest has been there for a while, which is to achieve scalable throughput with total ordering. And many systems, including LazyLog, which is an academic prototype, Carfu and Twitter's implementation, Meta's log device implementation, and all of these systems give you scalable throughput with total order. So in these systems, what you can say is you can combine the throughput of all the many shards, but you can still expect a total ordering across the records and across these shards. So you can say record 1 of shard 1 is the first record in the global log, and then after that, the first record of shard 3 comes, which gets the slot 2 in the global log, and so on. Right? You can establish a total order. So this is great. You can now achieve scalable throughput with total order. But the problem is that these systems often run into this high ingestion latency problem. Right? So I'll illustrate this problem with LazyLog, which is a reference implementation for many scalable logs. And the way this works is we need to understand like the different components of the system. So we have 3 big components. One is the shard, which is the unit where you store the data themselves. And I have chosen to show a primary backup shard here, which is basically saying that you use primary backup for fault tolerance within that shard. And then you have the clients, which are producing and consuming data off of the log. And then there is an ordering layer. The ordering layer, I want you to think of that as a small Paxos or a Raft cluster, which is fault tolerant on its own, but it is not seeing the data payloads. It is just seeing the metadata. So in LazyLog, what clients do is clients first write the data to the shards. So the shards are going to make it durable by replicating the data to their backups. And then periodically, the shards are going to talk to the ordering layer, saying that, hey, I have made these many records durable. Can you sequence them in the ordering layer? So the ordering layer is going to do that, and then it's going to send you the ordering information. Once you have the ordering information, you can respond back to the clients saying that, hey, this is the order for your records in the log. I'm done with the append. Right? So this, you can see, it takes 3.5 RTTs through the network, and it also has this batching interval because you have to batch records of the shards before you can talk to the ordering layer. Right? If you talk without this batching to the ordering layer, then you will overwhelm the ordering layer. There are other systems which are built around built in a slightly different way. For example, take Carfu. So Carfu, the way it works is, instead of doing durability first, you do ordering first, right? So the clients first talk to the ordering layer and ask for, hey, what is the next free slot in the global log? And then once you get that information, you can write those records to the shards, you can make them durable, and then once that is done, the clients are acknowledged. This reduces the batching interval delay, but it has to take 3 round trips through the network to get the data appended into the log. One key point, if you observe here, is that by the time the append completes, all of these logs complete 2 critical operations. One, they make the data durable, and then they also order the data, right? If you think about systems like Kafka, they also complete these 2 steps by the time they give you a response, but they're not establishing the total order, but they're just doing ordering within the shard. But it doesn't matter whether they are doing total order or per shard order, all of these logs today result in very high latencies for applications. And in our test beds, we have seen that all of these systems incur several milliseconds to ingest data, which is not the scale we are targeting. And this kind of directly impacts applications that we want to optimize. So there is this other new paradigm of building shared logs, which is this diskless architectures. I'm not going to go into the details of what is the benefits of doing this. But essentially, the brokers or the shards are now not replicated on their own, but they are depending on something like S3 for durability. So here, the way it works is the clients first write the data to the broker. The broker is still doing some batching. And then once it batches enough records, it writes to the fault-tolerant data storage, something like S3. And then it knows that these many records are durable. And it conveys this information to the metadata layer, which produces the sequence. And then you can finally release the responses to the clients. Again, if you think, when you get the response at the client side, both ordering and durability are completed by the time the appends are acknowledged. While this kind of an architecture is great for like high throughput and cost efficiency, it is not great for low latency applications, which is what our target is. And as you know, many applications require low latency for ingestion. Like for example, FireScroll is a database built atop Red Panda. It requires very quick durability. There are many other applications. And more broadly, there was a very interesting survey from Red Panda data in 2023, where they interviewed many practitioners using Kafka-like systems in the wild, and they interviewed 300 practitioners. And a third of them reported that ingestion latency is the primary latency metric that they care about in their deployments. So we had a very strong motivation to optimize this ingestion latency. So let's ask this fundamental question. Why is there this high latency in these systems, although they have been used for many years now? Well, we call this, we noticed that this is rooted in this very fundamental problem, which we call the eager ordering nature of these shared logs. What I mean by this is, the order is established eagerly when you append the data into the system. In other words, the record is bound to a position within the log during append. So in the next part of the talk, I'll show you how we can fundamentally solve this problem. So the key question that we're trying to ask in this work is, because we know that the eager ordering nature of these shared logs is what leads to high latency, can we somehow avoid this eager ordering, right, which leads to low ingestion latency, but you can still give the same ordering guarantees as the conventional shared logs would do, right? So we don't want to change the ordering guarantees in any way. We're still giving you the strict linearizable ordering guarantees, but we want to somehow avoid this eager ordering so that we can reduce the ingestion latency. So that's the crux of the problem. So perhaps this is the important slide of the talk, which is like, what is our insight? Well, the insight is that although linearizable ordering is required in all of the applications that we studied, in many of these applications, it is not required right away. You don't need to establish this order when you ingest the data into the system, but only later when data is consumed off of the system, right? That's the crux of the insight. And in many of these applications, Kafka-like systems naturally decouple the readers and the writers, right? Which means that, there is this natural gap between when you write data into the system and when you read data out of the system. So you could use that interval to do something clever. So based on that, our core insight for the design is that, based on this insight, a shared log can differ ordering when you're ingesting data into the system, but you can do this before you can serve the reads. And because there is natural decoupling between the writes and the reads, you can do this work before, instead of paying the cost upon every read. You can do that by the time the reads are already arrived. By the time the reads arrive in the system, you have already done the work. So LazyLog makes a simple but very powerful change to the shared log interface. In LazyLog, if you append a piece of data, it is not eagerly bound to a position within the log. But rather, what you get is, it gives you immediate durability. If you get a response from LazyLog, you know that your data is safe on 3 disks or 5 disks or whatever that is. And you get a guarantee that the record will eventually sit in its correct linearizable position by the time you read the log, right? LazyLog, in the background, establishes this correct order, but enforces it before you can read those log positions. Therefore, we preserve the abstraction of a durable ordered sequence of records. So we are not changing the external guarantees. So if you take a system and then look at it from an external perspective, it's no different than interacting with Kafka, but it's just that you get better ingestion latency. So in some ways, one way to think about LazyLog is that it behaves like a quantum system, right? So in a quantum system, you have these particles which are in the state of superposition. If you make a direct observation, it collapses and gives you a definite state, right? LazyLog also behaves this way. If you ingest data, it is in this wobbly state, but if you do a read, which is a direct observation, it resolves the order and gives you the data. So one thing that you might be thinking, this is like a nuts, right? This is a esoteric idea. Why would this help applications? Well, it turns out it is very, very naturally appealing to applications. Let's take an example. So FireScroll is a database that decouples writers and readers. It puts the data into the log. That's the writers. And then the readers read the stuff from the log, and then they construct database state, and then they can serve downstream queries, right? So in all of these, in this application, the writers don't need to know where their data actually sits within the log, right? But the readers must apply these updates in the correct linearizable order. That is still, that is not non-negotiable. That is, you cannot relax that ordering, but the writers don't need to know where their data is sitting in the log. And naturally, all of these applications, the readers are time decoupled, which means that there is an inbuilt lag between when the writers write the data into the system and when the readers read back. And this is not just one serendipitous application that I just made it up, right? Many applications are actually consciously designed this way on top of Kafka, if you think about it, right? This is popularly called the CQRS pattern or whatever, and if you see it, in retrospect, it's very natural to construct your applications this way, because you naturally decouple readers and writers, which leads to better scalable systems. The readers and writers can scale independently. You avoid the fate sharing between the readers and the writers, and you kind of minimize the performance interference. So it's a natural pattern for building applications. And we, in fact, also studied many applications which are built on top of Kafka. And in all of these applications, the readers are sufficiently time decoupled from the writers. And all of these applications can benefit from low latency ingestion. So LazyLog's interface is this, right? Can somebody say, like, what is the difference between the conventional interface and this interface here? Sorry, I'm used to asking questions in the class. Do you want to go? Mm-hmm. Right? Yeah, it is a physical position in the log, right? So, but there is a small change in the append interface. What is it? Yeah. Yeah, it does not return an integer now, right? Append does not return you where exactly the record sits. It just tells you that the record is durable, right? That is the only change that we make to the interface, right? And we don't return this index. And this actually suits many applications. We studied poured over GitHub repositories which are built on top of Kafka. And we looked at what do people actually do with this index that Kafka returns on an append. You guess what? Like, nobody cares about that. They just simply throw away that index anyway. And we also talked to another streaming vendor, WarpStream. They said that many of their applications built on their platform actually don't care about this index, which means that why do we actually need to return this index? So not exposing this index is what enables us to do the lazy ordering, right? Which gives us this hook to do the low latency ingestion part. So if you think about the LazyLog shared log, appends are always fast. You don't need to determine the order, right? But we can do the ordering in the background, and we can be very lazy about that. But if you're very, very lazy, then you have to incur this ordering cost on every read, right? So LazyLog does not do that. LazyLog ingests the data and then lazily keeps in the background ordering stuff. And by the time the reads arrive, you probably already have established the order. So you can serve the reads for free. But if it is required that the read requires the ordering now, you can force it when required. So if you think about it, there is like two portions of the LazyLog. So there is this purple portion and then the green portion. The purple portion is durable and it is ordered. And then the green portion is just durable, but you haven't decided what is the order for these records, right? And you're constantly moving stuff from the green portion to the blue portion, purple portion, via this background ordering. So appends, as I mentioned, are always fast. They happen in the green portion. If you read something in the purple portion, those reads are fast because you have already determined the order, right? But if you read something for a position for which you haven't determined which record must sit there, then you pay the cost of ordering at that point. But as I mentioned, in many, many applications, the readers are sufficiently time decoupled, which means that your reads are rarely going to be slow. But the interesting property of LazyLog is that even if that happens, your performance is still as good as the conventional shared logs like Kafka, right? So that's a very strong guarantee that you can get. So it's never worse than a conventional shared log, but it's most likely going to be much better, right? So the LazyLog idea is an abstraction, right? I have given you an idea. There are 1,000 ways of implementing this design, right? So I'm going to talk about like how we design two systems based on this idea, and then how it improves applications. So just an overview, we did two abstractions, two implementations of this abstraction. One is called Erwin, the other is called Erwin Black Box. Both of these systems give you linearizable ordering across shards. They give you with one round trip appends, which is basically saying if you had a producer into this log, you go through the network with your payload just one round trip, just one time, and then you get the correct linearizable ordering. This is theoretically the best thing that you can do, right? There is nothing more optimal that you can do. And both of these implementations offer about like 1 million appends per second in our testbed, but there is no reason why it shouldn't scale even more. But at this point, it gives you very, very low latency. The reason why we built these two systems is that Erwin can do this high throughput and low latency even for big payloads, whereas the black box version can do so only for small records. So I'll talk about why this is the case in a bit. But the practical advantage of the black box version is that you can take today's running Kafka clusters or Red Panda clusters, and then you can string them together, and then you can get total order with very low latency. That's a very powerful way to build or integrate LazyLog into your deployments. So let's talk about Erwin now. So Erwin has this goal of 1 RTT appends. So let's take a look at how it does this. As usual, you have the shards. I have used primary backup here for replication within the shards. We have the clients. And then similar to many shared logs, we have the sequencing layer. The sequencing layer, again, is a small cluster, something like Paxos or Raft, but we'll talk more about it now. So let's say the clients directly ingest the data into the shards. Now, it directly avoids our goal of 1 RTT appends because the shards are internally going to do some ordering. Let's say you run a primary backup that is at minimum 2 round trips to the network to make the data ordered within the shard and make it durable. So we cannot do this. So what we do is we break this black box assumption about the shards, and then we just disseminate the data in parallel to all the replicas within the shard. Right? This is just one round trip. You flood the data to all the nodes which are going to store the data. But now you have a problem. The problem is that it's not that your records across shards are not ordered. It's also that the records within the shard are not ordered. Right? So that's a crazy problem to have. So we cannot live with this solution. So what do we do? Well, what we do is we split the records into the actual data payload and a piece of small metadata that identifies that payload. And then we sequence this metadata through a sequencing layer, right? And the sequencing layer tells you this is the correct order for the records, right? So the sequencing layer now says that A goes before X, which goes before Z, which goes before Y, and we take this ordering information in the background, and then we can give it to the shards, right? And using which the shards can order the records in their local disks, and then they can serve out the reads. I kind of lied to you in the previous slide a little bit because I said, oh, we just sequenced the metadata layer, the metadata in a sequencing layer. But in reality, you cannot just do that, because if you just do that, what if that single mission fails? You lose the ordering data, right? So we have to now keep this ordering metadata itself in a fault-tolerant fashion, which means that you have to somehow make it fault-tolerant by something like Paxos or Raft, or put it on cloud storage or whatnot. But all of these operations incur inherent coordination and more round trips, and therefore they will lead to high latency. So our solution to this problem is that we just don't do any coordination. We just flood the metadata as well, just like the data, right? So we just send the metadata to 3 replicas in parallel. Well, you might be thinking, just one thing before we go here. So we write the metadata also in the same round trip as the data. So we are in parallel writing the data payloads, and in the same round trip, we are also writing the metadata pieces, right? And for now, assume that we are writing to all the replicas within the shard, the sequencing layer, but there is a different protocol for better availability. I'm not going to talk about that now. So now if you think about it, like once you have made the metadata pieces durable on the sequencing layer and the data payloads on the shard layer, then your appends have completed in one round trip. But you might think this is obviously wrong, and you would be right, which is basically that the metadata pieces can arrive out of order because there is no coordination, right? Like, so we have not coordinated anything, but so then, like, how is this protocol right? So the interesting part about this design, which is the most cleverest or the trickiest part of the protocol, is that we don't try to avoid this. We just allow it to happen, right? And then we have a protocol to reconstruct the correct order, even if the packets arrive out of order. I'll talk about that in a bit. So we allow these metadata packets to be arriving in different orders, but we will still give you the strong linearizable ordering guarantee. So here is the secret sauce, right? So the secret sauce is that if append B follows append A in real time, which is like append A finishes, you get an acknowledgement, and then append B starts after that, then it is naturally true that A will appear in all the sequencing replicas before B can show up in the log. This is true because like only after A has completed, you have started B, which means that for that A to have completed, it has to be recorded in all the sequencing replicas. So let's do this with an example. So let's say this is the actual ordering that happened in the real world, right? So there is A, which is concurrent with X, which is followed by Z and Y, which are concurrent with each other, right? If that's the case, then A and X can appear in different orders across the logs. That's fine, because they're all concurrent. But then once they have completed, if Z and Y started after that point, it is definitely, it's no way possible for them to arrive at any point in the logs. They must appear after A and X in the sequencing replicas. That's the key insight. So to break the order, right, concurrent commands can arrive in any order. So just to break the order, we'll just assign one person as the leader, right? And we can take that person's leader's order as the definitive order. So we can take this leader's order, we can propagate it to the shards, we can flood them with this metadata, and then they can start reading, serving reads based off of the given information. But the problem here is that if you have exposed your log in a particular order based on the information that you got from the leader's sequencing log, then you cannot go back and change your mind. If you do that, that would be a wrong behavior, right? So we cannot do that. So let's say if the leader fails, let's say the leader gives you this order that A is slot 1, X is slot 2, and so on. And based off of this, the shards have served reads to downstream clients. Now, let's say the leader fails. You cannot go back in time and then just change your mind. You cannot do that. That would be wrong. So we must preserve this exposed order. And the way we do this is via this very intricate protocol called the stable GP invariant. Stable GP stands for stable global position, which means that essentially everything up to the stable GP, there is no way the order up to that point will change, but anything after the stable GP can change, but we will just be careful to not expose that positions after the stable GP. So that's what we are doing here. So let's say we have this order here. We first give this order, that we take the leader's order and we give this to the shards so they can start doing the reads based off of it. But they can do so only up to the stable GP point. So now the stable GP is 0 because like it's the starting of the log. But if you have given this information to the shards and all of the shards have seen this ordering information, then you can garbage collect those entries in the sequencing logs and you can advance the stable GP. Stable GP is now 3. You can serve positions up to 3 at that point. So I have not talked about many failure cases in this protocol. Like for example, the metadata could be written, but not the data payloads in the other way around. And they could arrive at different orders and so on. And the Irwin system is built to handle all of these cases neatly and correctly. We have written pen and paper proofs to show that this system design is correct by principle. So that's great. This is the Irwin version, which works by modifying the shards. Remember, we modified the shards to disseminate the data in parallel to the primary and the backups. Now we are putting a constraint on ourselves saying that, hey, let's say we are running Kafka here for this shard, or Red Panda for this shard. I don't want to modify Red Panda or Kafka to use your systems or ideas. So how should I go about doing this? This slide is the answer. So here, what we do is, we can treat the shards as black boxes, so we won't modify them. We will just use them as is, right? And in our implementation, we have used both Kafka and Red Panda, and you can use any shared log for that matter. You can even throw in another version of a scalable log, something like Metas Delos or something like that. It's an abstraction for us. But Red Panda or Kafka wouldn't give you total order across these shards, whereas LazyLog's version would give you. So let's see how the system works. So let's say, like the Irwin version, if you write the data payloads directly to the shards, then that will not work because you have shard internal coordination, right? So that won't be one round trip writes anymore. So we cannot do that. Well, the idea is that then let's just write the payload itself into the sequencing layer instead of the metadata, right? So that the payload itself is flowing through the sequencing layer now, right? And we will run the same exact procedures as Erwin, but it's just that it's not the metadata that is flowing through, it's the actual payloads themselves. And we take this metadata and the data, and then we spread it to the shards, and we use the same procedure to the serve reads, right? And this is the reason why this version cannot scale beyond 1 million appends per second and it does so only for very small payloads, 100 byte records, right? And surprisingly, this is a very famous workload for WhatsApp workloads where like the payloads are very, very small. So if you have such a workload where your payloads are small, if you want like 100 million or 1 million appends per second, you can still use this design. But at some point, the NIC of those missions will become the bottleneck, so you cannot scale beyond that. So let me show some performance numbers and finish the talk. So what is exactly the latency benefit of lazy ordering, right? So here is a simple workload. We run 5 shards with 3 replicas each. We're just going to like append like 4 KB payload into the system and see what is the latency. So we are comparing it to a prior academic system called Corfu. And you can see the latency is microsecond scale. It's not millisecond. I'm not even trying to show Kafka here, but because it was like 100x slower, right? So Corfu is giving you about like 70 microseconds, but Erwin, because of its fundamental design to achieve the lowest latency possible, which is 1 round trip through the network, it gives you 4x or 3.5x slower latency than the best performing academic system before this. So if you show Kafka, these numbers will be very, very tiny, right? So it's 100x faster than Kafka and other logs. How do reads perform in LazyLog? Well, we will conduct the same workload where we not only append, but we will also read back the data. There is 2 cases here. So the readers could either lag behind the writes, which is the purpose-built use case for LazyLog, or we can also force the system into a bad behavior where the readers may not lag the writers. They are constantly trying to actively read the data from the log. So for many applications where the reads lag behind the writes, LazyLog reduces the append latency, and it does not pay the overhead on the read as well, because by the time the read arrives, you have already done the work of ordering. So both reads are, the read is preserved and writes are much faster. But even in the worst case, when there is no lag between the reads and the writes, if you study the performance properties, you can see that it is just inversed, right? When you append, you get very low latency. But if you immediately try to read it, LazyLog will incur the cost. But what we have seen in the wild is that many of these applications fit the first paradigm, not the second, right? So in many applications, the readers are naturally lagging behind the writers, so you would get a net win. And you can see that this is just inverted, which means that the end-to-end latency remains the same. We have also built a bunch of applications on top of LazyLog, a key value store, an audit log, a journal for stream processing systems, and so on. I'm not going to go into the details of these applications, but you can see if you build the same application on top of Corfu, you incur a particular latency, and LazyLog actually reduces that by about 3.5x. So to summarize, what I hopefully convinced you is that eager ordering nature of today's shared logs is fundamentally detrimental. It leads to high latencies. This is not actually needed for many applications, and readers are naturally time decoupled from writers in Kafka-based systems. And therefore, based on that, we proposed a new abstraction called LazyLog that fundamentally differs ordering on writes, but forces it only upon reads. And you can do this if you implement that kind of a system. You get low ingestion latency with very little overhead on reads and also on reads. So most of this, all of this work is publicly available. You can download the GitHub artifacts. You can download the paper here. Yeah, it's all public. You can just go and read it. So with that, I'll finish the talk. I'll just leave it here. So we are looking for industry collaborations. If you have streaming problems that you don't have time to look at, or if you think that needs some sort of like revisiting from first principles, we're all open ears. We can talk about some of these problems that you're running into production. We can help solve these problems from a research from first principles. So I'll finish the talk here. I'll be happy to take questions. Yeah.
If you're not using any coordination in the sequencing system, why do you need to do that right? Why can't you just use the unordered data store to know like what message?
That's a great question. So you cannot fundamentally do that. That's the bottom line answer. The point is like we want linear visible ordering for the applications at the end of the day, right? So you want to be able to somehow derive the order across these disconnected shards, right? The shards just like store the data that has been given to them. So the sequencing layer establishes this ordering information across the shards, but it does not do so in an eager manner trying to coordinate and find that order, what it is, during append time. But it records good enough information so that you can reconstruct that order even if failures arise. That's the way to think about it, yeah. Hey, yeah.
I'm glad then by the first law, because there is no such thing as a free lunch. That as you, so the good thing about the chart is it makes sense that you're making a trade-off between read and write time reconstruction. Just asking a very dumb question to be clear about it. This is also stable GP as an invariant defined that gives every reader the same total ordering, even when there's not non-causal reason. So it's definitely not like, as you're doing well over 1 million events per second and so on, we're doing microsecond action. We're not using a clock or something else to disambiguate it. Every reader up to that checkpoint, it's like a commit checkpoint in a transactional database, which is that every reader, under any circumstance, who talks to someone and asks for the reader ordering up to stable GP at any given point in time, we'll see the exact same ordering, right?
Yes, that's right.
So it's a total ordering over everything that happened in the system.
Yes, that's right. So to answer your point about like the first comment about like there is no free lunch, I agree largely. But there are cases where you can get most of the things. There is no free lunch when the readers immediately follow writers, right? So that there we will just simply shift the cost. But it's true that you.
Absolutely the correct distribution of real workloads. Yes, it's a huge improvement.
Yeah. So that's what like we are trying to say here, which is like, if Kafka is naturally decoupling your applications, then you should also exploit that fact to make your Kafka itself better, right? And to your comment about the stable GP, that's exactly true. So everything up to the stable GP point, the readers see them in the correct linear visible order. Okay, everybody should ask one question, just my lecture. Just joking, but more questions are encouraged.
Another one of the dumb questions is that under dynamic behavior, as you're scaling up and scaling out dynamically, so this is a systems kind of programming observation, with distributed hash tables and DHT-based scale out, there's often the question about there can be a pause, you need to double more replicas or add more things to the pool. It's not the same as a complete shutdown, but are there any quirks that have shown up in your understanding about edge cases as you scale up, scale down, or add new writers?
Oh, that's a great question. Actually, I didn't show that experiments here. So if you read the actual paper, we have a bunch of experiments where in the runtime, we would just like remove shards, just like halfway through the experiment, we would just shut down a shard. And then the system would not have any problems in terms of availability or anything like that. There is no even latency spikes. More interestingly, you can also add a shard dynamically into the system without any sort of reconfiguration required. So you can just say, hey, here's a new shard, can we get more throughput? And the system would do that. So we have some experiments in the paper which shows like dynamically, we can support dynamic additions and removal of shards. Other questions? Oh, there's one question there. Yeah.
This is just a fun anecdote, but while you're giving the talk, I was messaging a friend of mine who's at Pure Storage working on their distributed systems, and I was explaining some of the ideas. He said, oh yeah, this is like a well-known idea, it's called blind writes, and then he linked me to one of your papers. So it was kind of just funny, you know, and apparently they did a talk on it internally at Pure Storage, but anyway, just fun.
Yeah, that's great, yeah.
So going back to how append doesn't return the ID anymore, one of the possible use cases there is like if a writer or, wants to read its writes, right? And the and what it wants to read is something that's produced by another reader.
Right.
And so if it has the ID, you can say, hey, make sure I want to read from some state that has already processed this
Right.
particular ID. Is there a solution to that in this model?
Yes, yes. Our students actually built a version of the system which actually does this read you writes sort of semantics. How do you do that? Here is the correct way, which is probably less efficient, which is basically you ingest the data, right? You don't get an identifier, but then you can say, you can just perform a read with a large enough number, right? It won't tell you, like, it is going to tell you that that index is, like, doesn't exist, or you can just, like, fall back and then, like, find out, like, where is the log's tail. And then you can say, oh, just read up to this tail. So we do support a get tail call on LazyLog's interface, which means when you call get tail, you're going to get a number, which is roughly the number of entries which are durable in the log, right? And then you can say, oh, I know that I just got an acknowledgement for this I, so it is part of the durable set, so I can read up to that point. Yeah. And when you do that, we will resolve the order. Yeah. Great question. Yeah. Was another question? Yeah.
Where's the best place where discussions have been going on about this? So it's always exciting to get to the conference and present the paper and be there at the work with the people at the time that this may have been best published. But I was reading it, I didn't see much on Hacker News or on Reddit. You know, as everyone moved to Discord, like, where's your community discussing this stuff, and where's a good place to follow future developments?
That's a great question. So this is a sort of like a more higher level discussion that the research community and the developer community must settle on. So all of these papers that we publish are at academic conferences, and most people that show up here don't show up there. And surprisingly, I think I have not found an academic in this conference except for myself here today, right? Which is kind of depressing, but at the same time, I'm also feeling special, right? Because I'm the only person here. So usually, if you right, yeah, got it. Okay, that sounds great. So often, the best way to reach out to us is just looking at our papers and just emailing us. We have the email addresses there. The discussion sometimes gets into Reddit for some reason, and like some people like post a link to the paper and then the discussion starts. This has happened for like some of the papers that we have previously written. But usually you should be, we are very responsive to industry folks, right? So if you, especially if you have some money to give to us, right? And research grants or something like that. Right? You can put possible research gift in the subject. I'll respond to you in a minute, right? But yeah, definitely do reach out to our email. Yeah. We are thinking of putting together like a consortium within UIUC systems group to invite practitioners, specifically not academics, but just like people from the area, people who work at data streaming companies and so on, just to come there for a day. The only problem is that flying to Urbana, Champaign is a little hard, right? So you have to fly to Chicago, and then there is a very small flight to Urbana, Champaign, but you can always drive. But it'd be a fun day, right? Like we can arrange something like that, and then it would be good to hear from the industry folks. Cool. All right, yeah.